Well, thanks so much for having me here. I guess we're half real life, half virtual, but feel free to ask tons of questions and interrupt me all the time because it's much more entertaining for me that way. So yes, I will be talking about how not to generate random numbers, which is an extremely destructive title for a talk. I would rather, well, I don't know if I would rather be constructive. Maybe some of you would rather be constructive, but this is mostly about how things are messed up rather than how to fix them. So for that, I apologize. Anyway.
Apologize. It's not your fault.
Okay, well, okay, it's all of your fault. That's the lesson here. All right, so I figured I would start with making this concrete in case any of you weren't quite sure what we were here about. So here's a web page. Maybe some of you visit it, maybe some of you don't, but the relevant thing here is this little green lock on the upper corner and the HTTPS in the browser in the URL. So this is the browser telling us that we have a secure connection to this banking website, which we sure hope we do because we would rather not have our username and password stolen by some criminals on the way. We would rather not be visiting some fake Bank of America site. We would rather be visiting the real one. So these are the assurances that this cryptography is trying to tell us. So we can go in and click on this little block, and we can find out more information about the cryptography that it's using. So here we have SHA-1 with RSA encryption signatures, and then public key RSA encryption. We've got a public key, we've got an exponent, we've got a key size, whatever. So there's lots of things going on here, primitives. I took this screenshot a couple years ago, so I don't know, somebody with a laptop open might check if they've updated it. I think Chrome now gives you a little yellow URL if it's using SHA-1. Okay, so at the sort of very high level, what this thing is doing when we connect to this website is we're going to eventually be doing some RSA encryption. So here's the textbook version of RSA for you. We've got Alice and we've got Bob. So here, I guess, this is bob.com and Alice is you, despite the fact that there are no women in this room. Okay, so.
No other women.
No other women. Well, I don't know. I mean, you don't have any verification on me either. I could be a mirage. I'm Leia in front of you. Okay. So, all right. So hopefully you guys have all seen this before. But this is just to sort of fix ideas. RSA, everybody's favorite simple public key crypto system, also the first one. We've got a public key, which is a modulus n. It's the product of two large primes p and q. And we've got an encryption exponent e. And so the private key, really any of these values suffices, but basically the factorization of n gives you a decryption exponent d, which is e inverse mod phi of n. And then, okay, so if Alice wants to speak to Bob, she asks Bob for the public key that's contained in that certificate in the screenshot that I showed you before. Then when Alice wants to send Bob an encrypted message, like say her session key for the TLS session, she encrypts it by raising it to the ETH power mod n, hopefully with some padding so it's not horribly broken, so on and so forth. That's the ciphertext, and Bob decrypts it by raising that to the DETH power. Straightforward. So the only relevant thing for this talk is the fact that if you can factor the public modulus, then you get the private key. That's basically as deep into RSA as we're going to go. We also saw that RSA signatures are being used. For RSA, it's convenient that signing is equivalent to just doing the decryption operation. So if Alice is going to sign a message for Bob, she raises her message to the DETH power mod n, so using her private key, and then Bob can verify by checking that the signature raised to the ETH power mod n is the original message. Okay. Now, this isn't the only crypto that you use. Some of you might do something like this instead. So this is my SSH connection, trying to connect to my host computer. See, we actually have ENIAC at the University of Pennsylvania. There's a big piece of it on the first floor of the lab. And you can still log into it.
Oh, really?
Not the original one, sadly.
Yeah, you guys have it on a chip.
Basically,
you don't
yeah.
even want it in the museum.
Anyway, so here's our SSH connection. So if you're doing SSH, you're actually not using, well, you might use RSA signatures, although this one is using elliptic curve DSA signatures. But if you're using SSH, you are doing a Diffie-Hellman key exchange. So, yeah?
Has anybody in this room ever said no to that question?
Which question?
Yes.
I've said no.
Yeah.
Okay.
Has anybody else said no?
He has.
You said no. That's good.
That's like there's some unimaginable coincidence to find one, let alone two people that have said no to it.
Well, I said no, and then I immediately went and deleted the old fingerprint from my host file, and then I said yes.
We're so trusting.
You know, fingerprints, usability. Yeah. It's better than nothing, I guess. Okay, so at least sort of the textbook version of Diffie-Hellman. This, I guess, predates RSA, but if Alice and Bob want to guarantee on a shared secret in the presence of a malicious eavesdropper who's reading all the messages in between them, and they don't want to, say, generate a public key and send it back and forth, they can do the Diffie-Hellman key exchange. So in sort of the generic version, we've got a group which, say, is the integers mod sum prime or an elliptic curve group or whatever, and we've got a generator of that group. These are public parameters, and Alice and Bob exchange values g to the a and g to the b, and then they can compute this shared secret g to the ab. And the Diffie-Hellman assumption says that this is secure if an eavesdropper sees the transcript of all the messages g to the a and g to the b, they still can't construct this value g to the ab. They can hop in the middle, which is why we have this fingerprint verification that nobody ever checks. That's a little bit, I guess, outside of the scope of this talk. We're actually going to, discuss these values. Okay, so the security of Diffie-Hellman is based off of the discrete log problem. So a different cryptographic hardness assumption from RSA. There's also a signature scheme, the digital signature algorithm. This is the US federal standard. And its security is also based off of the hardness of discrete log, either in a group mod sum prime or an elliptic curve group. So we've got, for the digital signature algorithm, there's some public parameters which specify some group, and then you've got a public key, which is essentially what you would give out for Diffie-Hellman, although this group is different. And then the private key is the discrete log of the public value. So this is as deep as we're going to go into ECDSA, or into DSA or ECDSA, but it's relevant here.
There has been recent progress on the hardness of the discrete log problem, right? I mean, that changed, like, what, 3 months ago, 4 months ago? Maybe
So there was progress on small characteristic finite field discrete log a couple years ago, and they had really, really spectacular results. But these are not known to apply to large characteristic, like the prime fields that we actually use for crypto. There's also been some recent, like very recent work posted to the ePrint archive about elliptic curve discrete log, I think in binary fields. And there, it's unclear what's going on. But as far as we know, prime field discrete log is still the same hardness as it's been for the past few decades, if you trust that there's nothing else out there. So, other questions? Okay, so now that I've sort of given you an overview of all of the sort of crypto that you actually encounter in the real world, but I gave you sort of the textbook version of it, sort of the motivating question of all the work that I'm going to talk about is, what does this crypto actually look like on a broad scale in the real world? And the way that we're going to approach this problem is sort of 2 steps. Number 1, collect all the cryptographic data that we can. Number 2, look for strange things going on. This is very hand-wavy, but that's the general research program here. Okay, so step number 1 is collect data. The way that a lot of this work started was by collecting data on HTTPS. So browsers, locks, whatever. And This started actually from the SSL Observatory, which was a project which was run by the EFF. They actually nmapped the entire IPv4 space, and over the course of several months downloaded all of the HTTPS certificates they could, posted them online as a gigantic database, and people could download them. And so one day we decided to download them and see what was there, and it turned out to be way more interesting than expected. And subsequent to that work, some of my collaborators developed a much faster internet-wide scanning tool. So instead of using Nmap, you can, and it taking several months, you can instead scan the entire internet in 45 minutes or in 5 minutes if you have 100 gigabit uplink. So that's ZMAP. It's publicly available. You can scan the internet. They've been posting huge amounts of data online at scans.io. So if you want to repeat any of this research, you can go and download all of the public keys on the internet for the past several years. So here's a snapshot of what the internet looked like a few years ago. Something like there's about, if you basically nmap the internet, you see that about 30,000 hosts will have port 443 open, about 30 million hosts, about 13 million of them will actually successfully complete an HTTPS handshake with you. And of that, you can download certificates, and you end up with about 5.6 million distinct RSA keys, 6 million distinct DSA keys, a very small number of ECDSA keys, which has gone up since, but is still quite small because most certificate authorities don't issue these, and a few hundred GOST keys, which is a Russian cipher suite, which is not commonly used outside of Russia. So you can repeat all of this research as you would like. So that's something like what HTTPS looks like. For SSH, we did something similar. We scanned the entire IPv4 space on port 22 and initiated an SSH handshake with the hosts. It turns out that if you scan SSH, people really don't like that. They're willing to accept scanning HTTPS a little bit more than SSH. So you get a lot of complaints if you do this. Nevertheless, we've done it. Here's something like what it looks like. You find about 23 million open ports. Of that, about half of them will actually successfully complete a handshake, and you get 11 million RSA host keys. These are the keys that are used to verify the fingerprints. 9.9 million DSA keys. You can see these add up to more than the number of handshakes because you get a bunch, most hosts will give you many different kinds of host keys. You can choose which one you want. 1.2 million ECDSA keys. This has gone up since also. And 100 GOST keys. Then, okay, what other public key infrastructures are out there and easy to scan? There's PGP. So PGP, you can sign and encrypt your email messages. Back in the 90s, it seemed like a good idea to have this web of trust, and everybody would post online a nice database of who all their friends were with all of their public keys. And so you can easily download a repository of this web of trust data. And when you do that, you find a few million keys. There's actually far fewer RSA keys, probably because in the 90s there was still a patent on RSA, so it was not the default for PGP. But you do see a lot of Elgamal and DSA keys for PGP. Then there's Bitcoin. The Bitcoin database, or the Bitcoin blockchain, is also a nice source of a lot of cryptographic data because Bitcoin addresses are essentially public keys. Transactions require a signature. And so if you just download the blockchain and scrape it, you get a huge number of public keys and signatures. This data is, again, kind of old. So a couple of years ago, there were 15 million ECDSA public keys in the database and 22 million transactions. I'm sure that's doubled or tripled or multiplied by 10 or something since then. And finally, for people who like hardware, this is somewhat of an interesting example. So Taiwan has this really nifty sort of e-government infrastructure that they use to, or the citizens basically get these little ID cards with a chip in them, and it's a public key infrastructure for securely connecting to the government. So when you log in to pay your taxes, you can authenticate your connection using your little smart card chip, and you have a little reader that you can plug your card into the computer. And you can do all sorts of transactions with the government securely this way. And in order to facilitate this, and because the government wants other enterprises to use this infrastructure that they set up, they have this convenient public key infrastructure that's it takes the form of an LDAP database of public key certificates for all of these Taiwanese citizens. And so it is possible, well, they blocked it after we did this, but it was possible to basically download the contents of the entire LDAP database and get public keys and certificates for about 3 million Taiwanese citizens for their smart cards. So the keys never leave the chip here, but the public keys are distributed in certificates. Yeah?
Differential power analysis, though, is a reasonable avenue for as an attack vector?
So these cards are certified by all of the major certifying authorities. They're FIPS 140 certified, they're common criteria certified, so they are supposed to be resistant to all the sort of standard side channel analysis that you might do.
Are they, in fact? Have you talked to Paul Kocher?
I don't know if he's actually taken a look at these particular cards, but I'm sure whichever lab did the certification bought some of their products in order to certify them. So.
He did break a whole bunch that were certified.
Yes.
Well, we're going to break some of these too. In a different way. Okay. So yes, so I've been talking about all this cryptography, and this the title of the talk promised that I would talk about randomness. All right, so now we're going to start talking about randomness. And in moving from cryptography to randomness, well, okay, you can say, well, if you're going to generate a cryptographic key, you need some source of randomness in order to generate your key, because you want the attacker not to be able to predict the value that you chose for your key. Therefore, it's easy to say, let's use a random number. That will be unpredictable. And if you don't have a good source of random numbers, then an attacker might be able to guess what your private key was. That's okay. You can make that observation. It's not particularly interesting. So is this all that we can say? The answer is, of course, no, because I'm standing here giving
something
this
about like thousands and thousands of certain hosts were using the same key. There was a okay.
That's what I'm going to tell you about. So yes, what could you imagine is going wrong with bad randomness? Well, you might expect, if you don't have a good source of randomness, then you might expect to see repeated keys. So in the case of, say, an RSA public key, what would this look like? And as I said before, we have our modulus n and an encryption exponent e. And what is the value that we care about is if it's repeated? It's not e. So actually, basically, everybody on the internet uses the same value of e. For SSL, everybody basically uses the value 65537. And there's a few small ones. This is a log scale. So this is for all the certificates. You see a few people using small values. You see almost everybody using 65537, and then almost nothing else is used. So it is not a problem for the security of RSA if people are sharing the same public exponent e, because that value doesn't actually hide any of the secrets in the private key. What is a problem is if two hosts are sharing the same modulus n, because if they have the same modulus, then it has the same factorization, and then they both know the private key of the other. So this means that these hosts would share both the same public and private keys. They could decrypt messages that were intended for the other party. They could sign for each other, and so on and so forth. However, there are sort of more subtle problems that can happen. So if two hosts don't just share both prime factors, but if they share exactly one prime factor, of the modulus. So in this case, I have two moduli. N1 is p times q1, and N2 is p times q2. And so they share the same prime factor p. Then you can compute the GCD of N1 and N2, and that will be this value p. And now I've just factored both keys. And this is relevant because there's a big difference in the time to naively factor a number versus to compute a GCD. So for 768-bit RSA moduli, the current record was set in late 2009, published in 2010. It took about 2.5 calendar years for a team of academics using a bunch of their computing clusters to use the number field sieve to factor a 768-bit RSA modulus. In contrast, on my laptop, it takes 15 microseconds to compute the GCD of two 1024-bit RSA moduli. So there's a little bit of a difference here. Yes? Euclid's algorithm, or actually you can do better than Euclid versus number field sieve. So this would be a problem if it ever occurred. Now, okay, what about DSA or ECDSA? I can't actually say anything very intelligent about Diffie-Hellman keys. You know, if you share the same private key, you share the same public key, but I don't know any tricks. But it turns out with the digital signature algorithm, there is a trick because of the way the signatures are constructed. So similar to Diffie-Hellman, if two hosts share the same private key, they'll share the same public key. You can see this in the public value, and they could sign for each other, and they both know the private key for each other. However, the signatures themselves are randomized. So they contain a random nonce, and if this nonce is known, then it is possible for a single signature, and you know the public key, then you can easily compute the private key from the single signature and the known nonce. This is an interesting property for a signature scheme to have. And this also has the property that if your DSA nonce is ever reused to sign two distinct messages with the same public key, then you can easily compute the nonce, and from there you can easily compute the private key that was used. So if you ever once screw up with your DSA implementation and use the same value to sign two different messages, then your private key is forever compromised. So, okay. Now we have some things to look for in the wild in our gigantic database of keys. Let's look for them. Now, I'm going to tell you why this shouldn't work. So you can imagine an experiment. We take all of the RSA moduli that we collected off the internet. As I just said, we have many millions of them. And we compute the GCD of each pair of all of the RSA moduli. And if these RSA moduli are randomly chosen, then you expect nothing to happen. Okay, so if you say, okay, so we have M RSA moduli, they have two factors each, and if they are randomly generated, they're sort of the randomly generated primes, and we're essentially throwing two primes into random buckets at a time until we get a collision. So we know what time this will happen by the birthday bound, and we know how many primes there are of, say, 512 bits if we're looking at 1024-bit keys from the prime number theorem. And so the birthday bound tells us that after we have square root of m primes, or if we have square root of m, once we have like basically square root of the total number of primes, then that's exactly when we expect a collision, and it's pretty sharp at that bound. So if you plot this for 512-bit primes, here's this function. It's basically astronomically small until you get to pretty close to the number of atoms in the universe. And at that point, you do get a non-trivial probability of a collision. But anywhere sort of below here at reasonable bounds, you get almost nothing. Is that a question?
Well, the onset of astronomically small, since you're dealing with astronomically large numbers, the number itself is not, it starts to show up substantially before it goes to be probabilities approaching 1.
So yeah, I mean, you definitely need to worry if you're going to have a public key for every atom in the universe. And you might even worry if you have a public key for every atom in the Earth.
Square root of every atom in the universe.
No, This is the function. This is the probability of a collision that I've plotted here. So this is the square root of the number of the total number of primes.
But if we scale this so it's the actual number as opposed to the ratio of probability, then we might see an onset halfway up that curve.
This is if I take a randomly a collection of m primes randomly generated. What's the probability with my collection of m primes that I see a collision?
This is one collision as compared to a collision with my number.
Yes. This is a collision anywhere in this gigantic database.
Okay.
So a collision with your number will have probability 1 over the 2 times the number of primes, or 2 over the number of primes. And the probability of any collision follows the birthday bound. I may have done that.
It's a big number.
It's a big number. The upshot here is that this should never happen. Like, this is not something that you should worry about. You might think, well, okay, maybe you should worry. You still seem to be worried. But this is not something that...
At the square root of this number. It's not a real worry. But it might happen in talks like this one.
Well, it'll happen, but not because of this.
Just happened because of the lack of randomness.
75 is about half of 150, so.
Yeah.
Okay, I'll buy that.
Yeah. So there's this sharp transition between it not happening and it happening is happening at, yeah, square root of 10 to the 150.
Right, 75.
But basically, this should not happen. There's nothing funny going on with the distribution of primes. There's nothing funny going on with the number of prime numbers. If your keys were randomly generated, you have nothing to worry about even for 1024-bit keys, which you probably shouldn't be using anymore anyway. But, you know, nothing to worry about. Until the next slide. OK, so despite me proving to you, some of you, that this will never happen, we did it anyway. And OK, then there's the question of how do you actually do this computation? So the computation that we want to do is we want to take all of the RSA moduli that we downloaded and compute the pairwise greatest common divisors of each of them. And doing this the naive way, so for modulus 1 and modulus 2, compute GCD of the 2, check if it's not 1, and continue. This is a quadratic algorithm in the number of moduli that you have, and so you can estimate the amount of time that it would take, which is sort of just naively 15 microseconds per computation, and total number of moduli, choose 2 pairs, that's 1100 years, which is totally not out of the question if you have a giant cluster. But I did this when I was a postdoc, and so I didn't have a giant cluster. So we had to be a little bit more clever. And so the way that we were more clever, it turns out that there's a much more efficient algorithm for accomplishing this, which was published by Dan Bernstein in 2004. He put up a paper. It was actually an algorithm used for finding pairwise smooth numbers in preparation for a standard factoring algorithm, but we can repurpose it for our purposes here. It contains a bunch of sort of common tricks from the computational number theory community. And so the way the algorithm works, you can implement this in about 15 lines of Python. It's pretty straightforward. But basically, you compute this gigantic binary tree, which is called a product tree, where each node is the product of its 2 parents, until you get the product of all of the RSA moduli on the internet. This is a really big number. It was so big that we broke GMP in doing this. That's how big it was. Then you compute a remainder tree. You go back down the tree and mod out by the squares of each node in the tree. At the end, you end up with the product of everything mod each element squared. You can divide out by that element. And then at this point, we have basically the product of everything but N1. And we can take the GCD of that and N1, and that will tell us if everything but N1 and N1 have some non-trivial common factor.
With the divisions and all that, how long does this take to run?
So this is polylogarithmic. So you have a log number of nodes in the tree, and each the number of operations going across, actually sort of multiplication is it scales like n polylog n rather than like n squared in the number of bits. And so you're accumulating a bunch of polylog n factors, but the total number of operations on each node is within a polylog factor for each one. And so we have, basically, we start with like linear in the total number of moduli elements. And so each node in the tree takes like m polylog m operations with some polylog n, like the length of the tree.
15 lines of code? It's really only 15 lines of code?
In Python, yeah. We have more efficient code written in C using GMP, which is more than 15 lines of code. It's available online if you want to run this.
So Python's big num support is actually robust enough to do this?
It starts to break. So Python will work for like a few million keys. It'll start to break when you get to like 5 or 10 million keys, just because of memory management. It starts to die.
You spend all your time in the arithmetic routine in any case, so the overlying language doesn't make much difference.
Yeah, except that the big barrier here is that this is a gigantic data structure. This thing is huge. And so if this gets to be more than like your total amount of memory, then you have to start like reading, you either start paging or you have to read and write from disk. It gets a little bit unfortunate.
Did you do that?
Yeah, so we had to, this takes hundreds of gigabytes to store. And so we had to do all this mucking around, writing it to disk and whatnot. That was the part where GMP broke, is because they're using a signed 32-bit integer for the size of the numbers that you're running to disk, and we exceeded that.
Oh. A single number had more than 2 to the 32nd bits?
Yeah, the product of everything on the internet had, well, it was more than 2 to the 31.
I see.
Yeah. So, okay. Now that we've done this computation, or mentally, and you can do it, tonight at home after you go home, you can download some code, download some keys. All right, so what actually does happen? Well, it turns out that you compute the private keys for 64,000 HTTPS servers, so that's about 0.5% of the hosts on the internet, 2,500 SSH servers, 2 PGP users, and you discover a bunch of invalid keys that happen to be in the database, and 103 Taiwanese citizens. So that's not what you are supposed to be finding. What happens if you go through and look for repeated DSA nonces? It turns out that you can compute the private keys for 1% of all of the SSH servers with DSA keys and 158 Bitcoin addresses. Okay, what happens if you just look for repeated keys? Well, something like 60% of the HTTPS and SSH hosts serve non-unique public keys, which is kind of a shocking number because from a theoretical perspective, the first thing that you do when you do cryptography is like generate a random public key. And clearly the internet is not doing that. It turns out that there's a lot of reasons that are not vulnerabilities that hosts share public keys in practice. There are shared hosting situations where you have a single hosting provider and a bunch of who is either issuing presumably HTTPS certificates for all of their hosts, or you have an SSH kind of gateway that has a bunch of different IP addresses behind it. That's probably not a vulnerability. You have many organizations who register lots of domain names with the same key, so google.com and google.org and google.mx or google.fr. It's not a vulnerability if they share the same public key because it's one organization. They have they presumably have their own infrastructure. You also see a lot of expired certificates that are just renewed with the same key, which this is just standard practice. Although apparently after the Heartbleed vulnerability last year, when everybody was told, get a new HTTPS certificate, a lot of people went out and got new HTTPS certificates with the same public key that they had before. Sort of missing the point that their key might be compromised. So that case is bad, but in general, if you are just getting a new certificate, you don't need to change your key every year. There are a lot of common reasons that are vulnerabilities to share keys. A really common one is device default certificates. So a router manufacturer might just burn in a certificate into the firmware of the device. And so you will have tens of thousands or millions of devices out there that all have exactly the same keys. And people have reverse engineered these things and published databases of the private keys for them. The one reason relevant to us is things like entropy problems in key generation, which we can start to estimate, but it's hard to really get a rigorous estimate because of all of the device default certificates. And then there's also things like virtual machine snapshots. So if you generate a virtual machine and you set up everything the way you like it, you snapshot it, you distribute it to everybody on the internet, well, you already generated the SSH host keys. And so everybody who spins up an instance of that snapshot will end up with the same host keys. And we started to see a little bit of that. It's also very difficult to get proper estimates of that because I don't know how to tell if something's a virtual machine or not out there on the internet. So these are some massive, massive lower bounds just from basically hand counting places where these reasons were clearly identifiable. So default certificates for HTTPS, at least 5% of hosts are sharing keys because of default certificates or keys. For low entropy, I'm sure it's actually much higher, but 0.3% can be manually identified. This must be an entropy problem. It's not some kind of device default. And then for SSH, about 10% of hosts are sharing public keys because of either default or low entropy keys. Massive lower bounds.
So how do you isolate the low entropy situation? How do you discern? I'm not even seeing how this is happening, which is so you're leaving me in suspense.
Okay, it's kind of an aesthetic judgment. So I guess I didn't mention that here. If you connect to a machine and it says my SSH implementation is like this router manufacturer, and then if you look at all of the hosts that had that banner for their SSH implementation, and then you see a distribution that falls off like this in the distribution of what their public keys are, then you say that looks like an entropy problem rather than that they were building something in.
This is not a sharp impulse, it's a degrading curve.
It depended on the implementation. But if we saw that like everything shared everything from that identified itself as being from a particular manufacturer had exactly the same key, that looks like a default key. If there was some kind of distribution that looked like it came out of a random process, then that looks like an entropy problem. I can't prove it to you, but that's awfully suspicious. And then in cases where we definitely knew that what was happening was because of an entropy problem, then we could see some of these distributions repeated again. So this is kind of a qualitative judgment on my part. Okay. What did I do here? I broke my thing. Oh well. Okay. So here is, if you look at the most commonly repeated keys on the internet. So this is the 50 most commonly repeated RSA SSH keys. And you just say, what is their banner? What IPs are they being served from? Can we identify why these keys are repeated? Here's something like what you see. The most commonly repeated SSH key is from Verio, so a big internet hosting provider. My parents actually have an account on Verio, so I went in and checked whether I could see the private key, and I couldn't. So I decided it was not a vulnerability. The next several most common are all obviously devices, various kinds of routers and firewalls. And what you see as you go down is hosting provider, device, hosting provider, device, something else, or I'm not sure. And so nearly all of them were shared either because they were big hosting providers where probably they just manage their own infrastructure and it's not a problem, or it's some family of device that has some kind of baked in default key. For the TLS certificates that we factored, when we went and looked at those, the vast, vast majority of them were not browser-trusted certificates. So they were not signed by a certificate authority. Nobody paid money for these things. And the web pages for the two that had been signed by certificate authorities weren't active when we were looking at them. So the subject information for the certificates looks something like this. if you go and refactor all of the vulnerable keys. And so they say, okay, self-signed, system-generated, or they identify, here's a printer, there's a router. So these are all sort of clearly auto-generated certificates from various kinds of devices that list things like serial numbers. These aren't banks. So this is sort of a clue that what we were looking at was not sort of a widespread problem, generic problem in crypto implementation. It's a problem somehow isolated to devices, and in particular, things like routers and firewalls, which actually, you think the internet is real computers. It turns out that if you just scan the internet, what you see is devices. There's a huge number of things out there. So the Internet of Things is already here in some sense. So these implementation problems for devices, it also wasn't that there was a single family of device that was vulnerable, that had made some mistake. It was across nearly all of the major manufacturers. So every name in the industry that you can think of, we saw represented in the vulnerable keys that we found. So there were various kinds of network security devices. So these Juniper network security devices were more than half of the factored HTTPS certificates.
The base design that a lot of these devices are derived from, though, they share a lineage, and which is to say there's enough commonality in the family tree that even though they're different manufacturers, someone may have bought a license to someone else's design.
So a lot of these things are running some version of embedded Linux on some little processor, and there's a few distributions. I mean, you know, the generic thing that we can say is, okay, they're probably running SSH on some version of embedded Linux on some little version of some version of hardware that's specialized to them. That was sort of the most generic. But Juniper doesn't follow that. So Juniper has its own operating system, which is based on BSD. And there were actually several different versions of Linux. There were several different versions of SSH hosts and whatnot. So it wasn't all because of some shared family tree. There was a lot of shared keys because of shared family trees, but there were a lot of different implementations that were clearly having similar kinds of problems. So yeah, we identified devices from more than 50 manufacturers. It's every name that you can think of. And all sorts of interesting things like firewalls for power plants, cell towers, power grid things, HVAC systems, printers, the like.
This bodes very well for the Internet of Things.
Yes, that is a very astute observation. That,
don't forget gaseous centrifuges too.
I did not identify any centrifuges, thankfully. Hopefully I never will.
Do you attend DEF CON? I'm just curious.
I've been twice.
Okay.
Okay, so I want to talk a little bit about sort of the big picture of what these implementations are doing. Okay, so if you think of your little device, it wants to generate a crypto key. You plug it in, you turn it on. It says, I'm going to boot up my SSH process now. I'm going to generate my host key. Okay, so what does it need? Well, it needs to generate its host key now. And it needs a source of randomness. Where does it get it? Well, there's some, whatever this SSH process is, it's some application-specific pseudo-random number generator, hopefully coming from some library like OpenSSL. The way that this application-specific random number generator is going to generate numbers, well, it's going to take randomness from all the sources that it can, which are basically the time, the PID, and maybe the operating system entropy pool, because the operating system is kind enough to provide a source of random numbers. But it doesn't have access, the application itself doesn't have access to a lot more than that. Then, okay, where does the operating system get its entropy from? Well, it takes its inputs from, say, keyboards, mouses, hard disk timings, network interrupts, that kind of information. Okay. So if you think about these little devices, you plug it in, you turn it on, it starts its SSH process. It might not even be hooked up to the network. It doesn't have a keyboard, it doesn't have a mouse, and it probably doesn't have a hard disk. So all of the sources of entropy that the operating system was expecting aren't present. It might even be hooked up for the first time in the factory, and so it's never, it's not even done yet. Second, when the application decides to query for random numbers from the operating system, even if the operating system had access to entropy, it might not have actually incorporated it into its entropy pool at the time when it was queried by the application. And this was actually a vulnerability in Linux that we experimentally verified, that there was essentially a boot time entropy hole. So if you started up your Linux distribution, it would wait until it had a certain amount of entropy in order to mix that into the main pool for output. If you queried urandom or a devrandom or dev-urandom, because they were worried about the possibility of an attacker sort of carefully tracking the entropy sources. So you want to mix in lots of entropy all at once.
But they didn't block the random API until that entropy was incorporated?
So it will block random, but it won't block urandom. And so, I mean, this is, you guys all have beards. I assume that you all use Linux all the time. So Linux has these two random number generators. There's devrandom and dev-urandom, and devrandom says, I'm high quality randomness. You should think of me as, information theoretically secure, even though it's not. And dev-urandom makes no promises. It only says I'm the output of a pseudorandom number generator, but it never blocks. And if you read man random, it says as a general rule, dev-urandom should be used for everything except long-lived GPG, SSL, SSH keys. But the issue here is that the very conservative blocking behavior of random is a usability problem. So random will try to measure the amount of entropy that's going in and coming out and try to make sure that they never give out more entropy that came in. You can quibble about how good their estimation of entropy is. It's probably not very good, as some people showed a couple of years ago. But this is overkill, even for proper cryptography. All you care is that your pseudorandom number generator has been seeded once. You don't care about continual seeding. And because of that, this little router, it's probably never going to get an output from devrandom. So what's the developer going to do? They're going to say, well, screw it, I'm just going to use urandom. The difference between random and urandom is some theoretical academic concern that doesn't apply to me.
Well, pseudo is pseudo. I mean, you got to start somewhere, right?
Well, pseudo-random number generators are perfectly fine for cryptography as long as they are seeded with uniformly random inputs.
Once you've seeded them. Big enough.
Once you've seeded them with sufficiently large, say 256 bits of uniformly random inputs, then a cryptographically secure pseudo-random number generator is everything that you need for the rest of your life.
Sure. Well, part of that's an architectural question too, though, there. I mean, it's not just the fact that it's 256 bits, it's what the underlying representation of that can be exploited for vulnerabilities.
Well,
You're saying if you can get at the underlying hardware or the operating system while it's doing that processor, you can grab the right number or the seed.
yeah, so there might be other vulnerabilities if you can recover the state and the like, but assuming that those are not a problem, then...
During the initialization, there is this hole that you refer to.
Yes, during the initialization, there is this hole, and this hole is the problem. So here is a developer for one of the most commonly used SSH implementations on these little embedded devices, saying, I give up, I'm not going to use devrandom because it will never provide any output. So if system developers aren't getting seeds between boots nor getting any entropy from somewhere, it's their own fault. Give the problem to somebody else. Okay. So, right, I have established that there is this problem at boot time, which the Linux developers have fixed. They have issued a patch. They changed the behavior of Linux at boot time. It will be much more aggressive in incorporating entropy into its pools, and it will also take it from more sources now. So, post 2012.
BSD implementation similarly vulnerable?
BSD did not have nearly as widespread problems because they were better at seeding on boot. There were a couple of vulnerabilities in BSD several years ago where they had boot time entropy seeding issues, but those were resolved. So, Yeah?
About how far in the past, how long has it been since they patched this hole?
It was in summer of 2012. And they were extremely responsive. I was very impressed. Basically, like, we emailed them and had a response from Linus in like half an hour, and there were patches by the end of the day.
So your team pointed it out?
Yeah. Okay, so I've established that there's this entropy problem. I haven't established how this generates keys that we can actually factor. So at this point, you might believe me that there are reasons why we would see many, many repeated keys due to entropy problems in the wild. But why are we seeing keys that are sharing one prime but not both? Okay, so if you think about, here's a sort of cartoon version of how you might think to implement RSA in software. Your application might seed its pseudorandom number generator, and then it says, give me a random prime, give me another prime, multiply them together, that's my modulus. And so obviously if you haven't seeded your pseudorandom number generator, or it's seeded always with the same value, then you expect to see large numbers of shared keys. And these repeated keys are a sign that you might be vulnerable to a targeted attack. But this does not explain, since the pseudorandom number generator is going to be a deterministic process, why we might see P shared and not Q.
If the hole vanishes in between those two lines of code.
Yeah, so if you are adding randomness from some entropy source in between generating P and Q, then you might expect to share one prime but not two. But if you look at something like OpenSSL, it's not adding an obvious source of randomness. So what OpenSSL does is every time you get a big num from the pseudorandom number generator, it will add the current time in seconds into the pool, which does not sound like a very good source of entropy. Because the time has to be the same if you were getting the same seed out of the random number generator in the first place. So it turns out that due to clock drift, different devices can have slightly different notions of their CPU time versus the real time. And if the real time ticks on a slightly different cycle of the CPU than for the actual, than in the devices, then you can end up with just enough entropy to produce this nice distribution of shared primes that we were seeing in the wild.
Are you saying the remainder modulus, the clock tick, is of two devices relative to each other is holding as a constant? Is that what even?
I'm saying that there's a little bit of these devices, one might have its clock running a little bit faster than the other. And so if you imagine two devices here that both start up, they both think that it's Unix time 0, and then they start moving forward. And as they're generating their keys, the key generation process, they start with the same seed, and then they have to query many, many big nums in order to generate a prime. And as they do that, then one of them is running slightly slower than the other. And if the clock ticks on a slightly different iteration of querying a big num out of the random number generator, then they will see different values, and then the state of the random number generator will diverge from there afterwards.
This looks good, but I don't quite understand it yet.
Mm-hmm.
The machine comes up and it doesn't have a time at all, right? So
It thinks it's Unix time 0, and it starts ticking forward from there.
Okay. Now, how is it counting time? It's counting time in machine cycles.
It has some real-time clock on it.
Well, but they don't even all count in the small, the LSB. Some of them increment by some tick amount. In other words, they're artifacts in the least significant bits of the time of day that are not random when you sample.
So my picture here is that we've got a CPU clock and we've got a real-time clock. So the real-time clock gets powered starting from when you start it up.
Yeah, but if
And
you have a real-time clock, it would have a battery behind it, and it would know what time it was.
But it was never seeded with the time, because it's never been plugged in before. That's,
Okay.
I could be wrong about this. But
That scenario would explain it. But.
Yeah, and the concept is clear to me, and I understand the variability for all computers, and they can measure all computers. They're all different. But I want to know what you think of as a significant difference. What do you think a number that I can associate with the variability?
It's going to depend on the device.
1%, 2%, 3%?
Do I have
10%?
pictures
What's your concept of?
of variability?
Yeah, that's acceptable or necessary.
Well, in this case, I don't care what the variability is. All that I care about is that it's generating some distribution.
There's an entropy rate.
Yeah, there's entropy. It's going to vary a lot depending on the actual clock speed of the devices. I don't want this to be the source of entropy that I'm actually using to generate the keys. I want to have actually had a good seed. The manufacturers can use whatever value for exactness of their clock that they want, and that's fine, but that shouldn't be their source of entropy for cryptography, is my lesson.
Atomic clocks you can put on your PC board now.
Oh, that's the opposite of entropy.
Yeah. So we tried to model this scenario. If I guess you guys all say you believe me, but if you don't believe that this might happen, we actually took a normal PC, shut down as many processes as we could, and fixed a seed for OpenSSL and said, generate me a key. And if you do this many thousands of times, you see a beautiful distribution of different P's and Q's that get generated, depending on exactly where in the key generation cycle this second was ticking. And it depends on the speed and all sorts of other things. So. Okay, I'm getting low on time here. Should I like wrap up now, or should I keep going for?
You got to lay down.
And where are all the graduate students anyway today? They seem to be,
They're home
they're supposed to
watching.
get credit for this course, right?
They watch it on.
Oh, you guys are more fun than grad students. Okay, so now maybe you believe why we see factorable RSA keys. Why are we seeing these repeated DSA nonces? So the DSA nonces are being generated in real time during the actual sort of running of these devices. And even if you have a horrible little device that doesn't have any seeds on first boot, it's been up for some period of time when we actually were scanning the internet, and hopefully it's actually incorporated some entropy into its entropy pool by then. But it turns out that when we requeried a lot of these devices that were generating keys, what we found was that they were generating a deterministic sequence of nonces. And the sequence is coming because the application-specific random number generator is seeding itself once and then deterministically ticking forward, which is a perfectly fine model if you have a good cryptographic seed. It is not a good model if you don't have a good cryptographically secure seed. And so the reason that we were seeing colliding nonces in many cases was because you can imagine, say, 10,000 different routers, all from the same manufacturer, and they were all started with the same state, and then they got queried different numbers of times. And so we will see two nonces collide in a single scan if two of these 10,000 happen to be in the same state when we collided them. But if we go back and then ask for 100 different values from their pools, then we will see eventually more collisions. So this explained some but not all of the problems. There were a few manufacturers who just didn't understand that you needed to generate different values for every signature. This is apparently a not uncommon problem with DSA.
So the problem here is entirely in the seeding, not in the pseudo-random generator.
Yeah. It's pretty easy to generate a good cryptographically secure pseudo-random number generator at this time. I mean, AES encounter mode is great, right?
So did you have any trouble finding appropriate representatives in all of your 50 vendors?
Oh, it was terrible. It was a horrible experience. I've got a slide that summarizes this at the end, so you'll hopefully get to. Okay, so what about these smart card keys? So some of you were very interested in these smart card keys. If we went and looked at the primes that we saw when we actually factored these keys, this was the most common factor that we saw. This does not look like a random number.
First prime after C?
Yes, this is the first prime after 2 to the 511 plus 2 to the 510. So they clearly have some other issues. The next most common factor is this value, which isn't quite the same, but you see this is also not quite a random number either. It's not quite periodic, but it's like pretty close. And basically by extrapolating patterns, so this is actually, it turns out to be a repeated bit pattern, but they were swapping some of every 2 words in the representation. So by sort of extrapolating patterns of that form, incrementing to the next prime, we factored 80 more keys. And also by using some more fun lattice-based math to break things that had some bit errors there. Okay.
Of course, this could have been written by the Taiwanese government so that they could break things.
It could have been. A lot of the sort of comments on the internet were like, oh my God, is this an NSA backdoor? It's most likely not.
While I'm on that course, since you know Dan Bernstein pretty well, do you have any sense of whether the elliptic curve standard, the NIST standard, has weaknesses that are not found in the Bernstein curve?
There are no publicly known vulnerabilities that these curves could have. So these curves don't have any of the publicly known properties that might make it easier to solve the discrete log problem on them. But
maybe other properties that are only known by.
She's being coy.
so
Okay,
That's the only answer I'm going to get.
Yeah.
Definition of publicly used.
Yeah, that's the only answer that we can really give, right?
Yeah.
I mean, you can quibble about the random number generation process, which is part of what Dan and Tanya are sort of doing, is that the provably at random parameter generation process that they used is not at all provably at random, which is a little bit annoying. But we don't know of anything. They're probably fine. I mean, you can use curve 25519 if you trust Dan more than the NSA. Yeah. I find it, I mean, it's like NSA with whatever gigantic budget that they have and however many 100,000 employees, and Dan.
Well, except you have to look at the NSA as budget of X and a budget of minus X in the other half of the house. That may end up with an aggregate budget of 0.
I think your point is that the NSA will require an exponential number of dollars to keep up with the ingenuity of a few scholars.
Well, but do you really want to have the security of the entire internet rely on one guy who could be hit by a bus tomorrow? I mean,
Well, that's not necessary. I mean, we can vet his work, but it will require an exponential number of dollars for the NSA to compete with that. They will require millions and millions of mathematicians to basically counter a few good crypto engineers. They don't realize this yet, but they're going to find out.
okay, so how many NSA employees is Dan worth?
How do we know he's not an NSA employee?
He might be an NSA plant, yeah. The best backdoor that they had. Dual ACDRBG was like not a very good backdoor, right? People saw through that one within a few years. But the NSA curves, we don't have anything on them. Or the NIST curves, sorry.
Sorry to distract you.
It's more entertaining. All right, so these smart card keys. You guys like smart cards. So, all right, why are these government certified smart cards generating private keys? We know how to generate good random numbers in hardware. So all of the standards, so the FIPS 140 standards, the common criteria, whatever, they sort of have a list of things, best practices that you should do. The designers should characterize the entropy. There should be some testing of the entropy source at runtime to double check that it's not outputting all zeros or repeating values or whatever, and then you should post-process this entropy source by running it through some kind of PRNG, hash function, something to whiten it, right? So this is basically like the big picture idea of how you should generate your random numbers anywhere really, but also in hardware. And these cards that are generating primes that look like that are clearly doing none of these things, even though they were claimed to be FIPS compliant. And so we actually never got our hands on one of these cards, but our hypothesized failure was that there was actually a hardware failure in the underlying entropy source that would fail in some situations. So our hypothesis is that a lot of times these cards are doing they have some kind of like ring oscillator that should have some kind of chaotic interaction. But if it got stuck, then it might sort of output these periodic values that we were seeing. And so if in some situations it's outside of the proper temperature or it got hit by a hammer or something, maybe it would get stuck. And we would see actually values where it would get stuck and then it would get unstuck. So that's one problem. And then the card software was actually not being operated in FIPS compliance mode. And so that meant that there was no testing and no post-processing of the random number generator output. Yeah?
So you used a ring modulator as an example. Do they use noise diodes some of the time?
I don't know.
Because there's so much noise in the world. It's just amazing to me that they don't just put a diode there and sample it and so on.
Well, it's not uniform noise, though. You have to widen it.
It doesn't have to be terribly uniform.
As a C?
Apparently, sometimes she's pointing out, it gets stuck, though, which is
Right.
to say, some random number generators may not go into their pseudo-equilibrium, so they don't generate this. Usually there's a metastable process in these things. They servo flip-flop at sampling, and they wait for the metastability to fall out. And if the system isn't initiated.
Yes. For those of us who don't write all our programs randomly, the fact that they do behave randomly on their own. So we have unintentional randomness, which is far too common, and now you're telling me that intentional randomness is far too rare.
So the problem, what you want is no randomness when you don't want any randomness, and you want perfect randomness when you do want randomness. And
You
sadly,
want reliable randomness.
yes, and sadly the real world is somewhere in between. I think there's this.
Also, because of the hardware question, you also have to add the operating system comment up. You also want this as an atomic operation.
Mm-hmm.
Yeah, we actually, one interesting thing with Linux is that we saw a little bit of entropy coming from, basically, it was not an atomic operation. And so different processes were reading the pool at slightly different times and getting some amount of randomness just from sort of non-deterministic behavior for when different processes would be reading. Even when the stream that was being output was continuous or was deterministic. So unintentional entropy. I think the big message here is that a lot of programmers, you want to think about entropy as something you press a button and you get entropy, but it turns out that entropy is actually something like an environmental resource that you have to wait for, that you're not guaranteed. But that's not the model that all the people writing programs want to treat it as. You want it to just be a function call rather than some kind of blocking resource.
A lot of those folks are not aware of cryptography.
Yeah, well, we don't want normal people to have to think about cryptography. Cryptography should be one of those invisible, magical things that just makes everything function. And the fact that developers are having to think about cryptography is also a serious issue. Okay, so what about PGP? We should expect the developers of PGP, they should be paranoid. They are using dev random to generate their keys. Why are we seeing factorable keys? It turns out that this was probably not like the PGP developers' implementation. It was a different plugin that was generating these vulnerable keys. Both of the keys were more than 10 years old. They were generated by German speakers. German speakers were unhappy to find out that their keys were compromised, but they were not currently being used. So hopefully it is an implementation error in an implementation that's no longer being used. And this is a rare implementation error. For Bitcoin, there's actually been a number of different incidents. There was a Java random number generator vulnerability that was publicized in August 2013. They were not renewing the state of the pool when the process forked, and so different different processes can end up with the same pool state and then generate the same nonces. We also saw a bunch of test implementations of people who are sort of obviously not putting values or the correct, they were just putting in all zeros or whatever. There is a particular Bitcoin address that has been systematically searching the blockchain for the past several years for repeated nonces and systematically stealing all of the Bitcoins from anybody who ever repeats a signature. So.
I see. 59 Bitcoins.
This is an old number. I have no idea how much they have now. But yeah, so this means that math pays. Not as much as it used to, but it pays some.
It's a garbage collector.
Okay, so you were asking about the disclosure issues. This was an interesting process for me. So I personally wrote email disclosures to 61 companies. Of those 61 companies, which are it's like a random sampling of tech companies, including all of basically the major names, 13 of those companies had some kind of security team contact that I could find on their website. The rest of them I had to just guess. So we guessed, I don't know, tech support and what else?
We got through to some of them.
I did get through to some of them. So ultimately, I ended up receiving some kind of response from 28. Some of those came only after CERT got involved. I didn't realize that I could just, go to CERT and say, please contact these companies for me. I have too many to contact. Since then, 13 of them have told us that they have fixed the problem. 5 of those published some kind of public security advisory. So one of the companies contacted ICS CERT, the Industrial Control System CERT, because they made industrial control systems to report the vulnerability. And at that point, ICS CERT contacted us and asked us to verify this. And we said, we have all these other companies too. And so they helpfully helped chase down several of the companies who hadn't responded before. And so they were very helpful in this. As I said, the Linux kernel has been patched. They were extremely responsive. And since the original publication, we have seen a decrease in the number of hosts serving factorable keys.
So is that number 28, is it before or after the CERT organization helped you with the contact?
After.
So what's left? If you add, I don't know how many of these things to add up, or how many overlap out of the 61. Are there 20 left?
So there's 61 minus 28 who have never responded to us. Maybe some of them fixed it, maybe they haven't. So the 28 includes everybody who told us anything ever. That was anything that sounded like a human response.